Hi, lovely people of the world. Um, Today, we're going to take a very quick look at what entropy is and how we can sort of look at it from a layman perspective and also derive it. I'll be going about the derivation by considering information and then multiplicity and then Stirling's approximation and then um, yeah, we'll finish with the derivation. Let's get started with the layman definition of what entropy actually is. Here we have it. This is essentially the layman definition. Entropy is the randomness in the information being processed within your data. It is also known as the average information content within the data. Um, let's get to entropy. To understand entropy properly, we need to first start off with the concept of what information actually is, because here this you can see that it says the randomness of information, but how do you quantify what information is? So the, there are a couple of very important assumptions that we make with respect to what we want information to be and what we want information to look like. And the two assumptions that essentially these two bullet points here. The first one being that um, low probability events will have high information and high probability events have low information. So probability is essentially a number between 0 and 1. So when your probability tends towards 1, you are if you're very certain about an event, you aren't getting any information about that event because you're certain it's going to happen. And when the probability is tending towards 0, then it's a very unlikely event. So for those of you who are interested in black swans, well, um, this is low probability events are sort of like black swans, and they sort of give you high information. That's the first assumption of what we want information to look like. And the second is the information from two events, X and Y, which are completely unrelated to each other. The total information needs to be the information gained from each of these systems separately. So there is an additive property over here. That's very important. Now, if you just think about these two assumptions, right? If you look at the second assumption, it says that the information from two unrelated events needs to be the summation of the probabilities. Summation of the information um, gained from each of these systems. We know that in probability, when two events are independent, the joint probability of both of them occurring together is the product of the two individual probabilities. So we have probability of x comma y equal to p of x into p of y. But over here, we want information to be we have this assumption of, we know probability is this, but information is got to be it needs to be the addition of each of these systems separately. And one function that sort of should come to all of your minds quite quickly is the logarithm. Logs have a very wonderful property of, hey, you have log AB is equal to log A plus log B. So that sort of solves the problem of, hey, you have probability, two individual probability systems over here. So you just have, if you have a joint probability distribution, or rather a joint probability of x comma y, that just becomes px py, but then the log just makes it log a plus log b, which is what we want. So you can see from here that that's sort of the very the layman way of sort of understanding it intuitively is that, hey, okay, logarithm makes sense, and we know log is sort of like this, and if you look at that between 0 and 1, it goes downward. So we take the negative log so that we get an upward curve, because it would not make sense if information is just negative all the time. This negative logarithm is essentially because probability is a number between 0 and 1. So it's a decimal, and decimals are the logarithm of a decimal number is negative. So when you take When you take the negative logarithm of a negative number, you get a positive number. And so that makes sense from an information perspective, that the information needs to be positive. So you have information which is small h of x is equal to the negative logarithm of p of x, and this is to the base 2. So when it is to the base 2, it's called, we tend to look at it as bits. One other reason why, bits is such a nice way of sort of looking at it is because Shannon showed that, hey, information is, this negative logarithm of probability of x is also like the, is also the number of bits that you can use to sort of like, let's just say, well, what I'm trying to say is the negative logarithm of the probability is the information, and that sort of like sets us up very nicely for the next definition, which is actually entropy. And entropy, as the second line over here just says, it's the average information content within the data. So that is the summation of the probability of the information. Let me repeat, that's the summation of the probability of the information. So here that is the summation of the probability of x times the logarithm of the probability of x. What entropy sort of is it is just the lower bound on the number of bits needed to transmit the state of a random variable. That is what entropy is. So when you put it, when you take the logarithm to the base of the base of 2, we denote it via bits because you have a 0 and 1. If you take it to the base e, which is 2.728, then that is called nats. And well, if you take it to the base 10, I don't know why you would take it to the base 10. Maybe you would, maybe it is a very big number, but if you take it to the base 10, then you just have digits over there. Decimal, let's just call it decimal, the decimal system. Anyway, so you can see that, and yeah, Shannon was the one who sort of gave us this idea of entropy being the lower bound of the number of bits needed to transmit the state of the random variable. So now we're done with, the spoilers are done. These are the two equations that we are very interested in. The remaining part of this talk is just going to be diving a little deeper into entropy and how we can derive it as well. And you can see over here that this is the graph of the negative log x. You can see that for log, when probability is 1, the logarithm of that is 0, and when it is tending towards 0, it shoots up towards infinity.